So good morning students. So please type in the chat box, am I audible? Yeah, so please type in the chat box, am I audible, and is the screen clearly visible to all of you? So please confirm the audio and video of this session. Audible and visible, sir. Great. Okay, so let us fine. So let us start this session actually. So this is the first lecture on this open system analysis actually. So we are into the 5th module of this course, open system analysis. Now if you see in this particular lecture, I am going to introduce you control volumes. Okay, so basically the open systems, it is something similar to the fluid mechanics case. Basically we see whenever we talk about control volumes, the mass balance or the energy balance, they remain the same. Okay, and energy conservation of open systems. So we will basically look at the conservation of energy with respect to open systems. Last time we have seen with respect to closed systems. Now we will see with respect to the open systems and steady flow energy equations, SFEE actually. Okay, so we will see steady flow energy equation. So when it will look at this energy conservation equation and we will apply that energy conservation equation to steady flows. Okay, and after a bit of discussion in the next lecture and in the advanced lectures, we will talk about unsteady flow energy equation as well. Okay, so we will look at some part of unsteady flow energy equation and then we will proceed from there. Okay, so before straight away going for that, let us see in the last lecture we have talked about a bit of heat interactions. So let us write certain formulas regarding that. So we have seen Q1 to 2 in a polytropic process, PV power n is equal to constant. Then we have seen this is equal to gamma minus n upon gamma minus 1 times of work interaction, and work interaction can be written as P1 V1 minus P2 V2 by n minus 1. Correct. So this is the work interaction generally in this case. So we have directed this expression gamma minus n upon gamma minus 1 into P1 V1 minus P2 V2 upon n minus 1 actually here. And also we have seen the polytropic specific heat. Polytropic specific heat. So basically C poly is equal to characteristic gas constant times of gamma minus n upon 1 minus n times of gamma minus 1 actually here. We have seen that and we observed that when 1 less than n less than gamma means basically if you see whenever 1 less than n less than gamma, this C poly is negative, and when n is greater than gamma, then we observed that this polytropic specific heat is positive actually. Okay, so this is positive. Clear? So C polytropic is negative and in this case the C polytropic is actually positive in this case. Okay, and now if you so basically these are the things that we have written, and using these formulas we can generate for constant pressure, constant volume, isothermal process, adiabatic process, we can generate the results using these simple formulas actually. Okay, and now if you see so after that bit of discussion we started solving some problems, and I think some 3-4 problems are left again. We will solve those problems and then we will start the open system analysis. Okay, so in the quickly some 30-35 minutes we will solve these problems. So let us continue to solve the problems which we left in yesterday's class. Okay, so then we will proceed for open system analysis actually. So let us solve this. The ratio of heat interaction to work interaction in polytropic process undergone by a diatomic perfect gas is 1:4. Okay, so let us see what they have given. There is a polytropic process. So let us suppose PV power n is equal to constant. PV power n is equal to constant actually here. Now the gas is diatomic gas. So if this is diatomic gas, then gamma is equal to 7/5, which is 1.4 actually here. Okay, so gamma is equal to 1.4 actually, which is 7/5 of course. Okay, now they are telling you the ratio of heat interactions to work interactions. So basically if you see Q12 by W12 is 1:4, so 1/4 actually. Okay, the value of polytropic index is dash. So first of all, if you want to calculate polytropic index, we know that heat interaction is equal to gamma minus n upon gamma minus 1 times of work interaction, correct? So basically this ratio will be equal to gamma minus n upon gamma minus 1. We have seen this relation that heat interaction is equal to, like here we can see in this formula we have seen this term corresponds to work interaction actually, correct? So now we have seen the work interaction calculation. So this is work interaction in the process 1 to 2. Okay, so this value is 1 by 4, so gamma is 1.4, it's already there. So we have to identify what is the value of n actually. Okay, so let us calculate this. So if you calculate this, implies 1 by 4 is equal to 1.4 minus n by 1.4 minus 1, which is 0.4 actually here. So what is the value of n actually in this case? 1.4 minus, okay, so this is 0.4 by 4, 0.4 by 4 actually. Okay, so simple equation, one unknown, you can simplify. 0.4 by 1.4 is equal to 1.4 minus n. So n value is equal to 1.4 minus 0.4 by 4. So if you simplify this, you will get the value of n actually, which is the polytopic index in this case, correct? So this is the value of n in this case. So let us see, there are some 4 options which are given. So if you simplify that, then 0.4 by 4 is nothing but 0.1. So 1.4 minus 0.1 gives you 1.3. That's it. Simple calculation. 1.3 is the correct answer in this. Okay, so 1.3, which is in option C, is the correct answer. Okay, but remembering this gamma minus n by gamma minus 1 is generally, I remember only this polytopic process. Like generally, if I want to solve any questions in heat transfer, generally I keep in mind this particular thing, so that I can know what is the work interaction and the relation between heat and work interactions. Okay, and in case of constant pressure, we have seen work interaction is equal to, when you put n equal to 0, gamma minus 1 upon gamma into q actually. Okay, so that's how we can identify this using this simple polytopic expansion results. We can generate for any other process in easily. So this is a simple question actually. So n value is equal to 1.3 in this case, and this is the simple small calculation that we can do for one equation, one unknown. Generally these kind of questions can be asked for 1 mark in a GATE examination, so we have kept a question. Okay, so let us solve this question. Next, an insulated rigid tank is divided into two equal parts by a partition. So let us see. There is a tank, rigid tank, actually it's a rigid tank, correct? Oh, just a minute. Fine. So there is a rigid tank, insulated rigid tank. So it is insulated as well and rigid. Fine. Insulated and rigid tank. Now this is divided into two equal partitions, into two equal halves actually by a partition. Okay, so let us suppose you have the partition here. So let us suppose if this is, each part is having a volume V, for example. Okay, this is volume V, this is also volume V, so that it is 2V, it is into two equal partitions. Then one part contains 4 kgs of an ideal gas at 800 kilopascals and 50 degrees Celsius. Okay, so this consists of, let us suppose, 4 kgs of ideal gas, 4 kgs of ideal gas at 800 kilopascals and 50 degrees Celsius. This is 50 degrees Celsius. Okay, while the other part is evacuated. So this is evacuated actually. Evacuated means there is a vacuum in this. Okay, no mass is actually present in that. It's a evacuation. Then in that case, the partition is now removed and the gas expands into the entire tank. So if you remove this partition, then what happens? Since there is vacuum here and there is some gas here, this gas will diffuse and the total container will be occupied by gas now in this case. Then which of the following is true actually? So first of all, if you see, generally this is called free expansion. Normally we have seen, whenever you are calculating work interaction, W is equal to integral P dV. This P is nothing but the total effective load against the movement of the piston. Yes or no? When you are writing this expression, you have, how are you getting the value of P actually? If you see, when you draw a free body diagram of the piston actually, look, I'm just giving you some small understanding here. So see, whenever you have this piston, when you have this small piston actually here, then in that case if the gas pressure is P, we are writing work expression as integral PdV, and if you calculate this P, what is the value of this P? This P corresponds to the total load against the movement of the piston. Yes or no? This P is actually pushing the piston, but during the movement of the piston at any point, the pressure acting on the piston is effect of the total opposing load acting on the piston. Yes or no? Means to the movement of the piston, whatever is the total forces in form of atmospheric pressure or weight of the piston. So in balance to all these forces, this P is acting. So this P which you are substituting here is the pressure of the gas, and that pressure of the gas is mathematically equal to the total resisting force. Means if you draw the free body diagram of the piston, if you draw this free body diagram of the piston, for example, if you have pressure P here, then you also have P atmosphere, P atmospheric local, and then weight of the piston maybe, so weight of the piston. Then in this case, if you write the expression for P, P is equal to P ATM local plus weight of the piston upon area of the piston actually here, correct? So area of the piston. So you know this P is equal to P ATM local plus weight of the piston divided by area of the piston. Now try to understand this very carefully. This P, what you are writing in this integration, is nothing but pressure of the gas, but at any instant the pressure of the gas acting on the piston is equal to the net effective downward forces that are acting on the piston, or downward pressure balance actually. Now this gas is doing a work against this complete pressure. Yes or no? Correct? Because this is the atmospheric pressure, and this also is some dimension of pressure actually, which is due to the weight of the piston. So whatever the pressure of the gas at any instant, that pressure is nothing but the total resistance, which is equal to the downward resistance. Means whenever the gas is expanding, the gas is doing work against this complete load. Now please tell me, in this case it is vacuum. So whenever there is a vacuum, if you remove this partition, for the expansion of this gas, is there any resisting load from the right side? So please type in the chat box. Whenever there is evacuation on the right side, if you remove the partition, if the gas want to expand, look here, when the gas want to expand, there is some net effective load which is acting downwards. To overcome that load, the pressure of the gas is acting on the piston actually to move the piston. So, but in this case, whenever you remove this partition, actually, whenever you remove this partition, for the expansion of this gas, is there any restriction like in this case? No, correct? There is no restriction. Then can you please tell me what is the work interaction? What should be the value of this external resistance that is acting? What is the value of this external resistance which is acting in this case of free expansion? What is the value of that P? 0, correct? So therefore, in case of free expansion, so this is a free expansion. This is called free expansion. Free expansion. So this implies work interaction in expansion is equal to, so W is actually equal to 0. Work interaction in case of free expansion is 0. Work interaction in case of free expansion, in case of free expansion is 0 actually. Okay, so this is one very important result, and understanding why this is 0 is very much important. Okay, because many times people mug up that work interaction in free expansion process is 0, but why it is 0? People explain this also wrongly sometimes. What they tell you, they'll tell you that P is the pressure of the gas. If they'll tell you that P is the pressure of the gas, here also gas will have some pressure. It's 800 kilopascal, such a huge pressure, 8 times the atmospheric pressure, but it's not actually the P. What we are substituting is this P, which is mathematically equal to the resistance. In actual case, if you want to do some work, let us suppose if I want to lift this body, okay, then against gravitational force I am lifting this, yes or no? Let us suppose if I am moving this body, against my friction I am moving this body, okay. So that's why similarly work done is always against some external resistance for the movement, okay. Like this, in this case, whenever the piston has to move, then definitely this atmospheric pressure plus these things, all they contribute for some internal, some external resistance on the piston, and the gas is actually doing work on that piston, okay. So this P, what you are substituting is the pressure of the gas, of course, but that is mathematically equal to this particular resistance, okay. This is what we cannot find here. So basically there is no external resistance, that's why work interaction in free expansion process is always 0. So please keep this point in mind. This is one of the very important understandings again, okay, in thermodynamics point of view. So if you check out the options, first option, work interaction is 0. Yes, this is a free expansion process, so definitely this option is correct option. Work interaction in this case is 0. Next, change in internal energy is non-zero. So first of all, let us see. If you apply, so let us suppose if you remove the partition and the gas completely occupy this, then if you apply first law of thermodynamics, we see Q in, or generally energy in minus energy out is equal to change in internal energy, because it's a closed system and stationary system. Now whenever this system is insulated completely, so let's say if tank wall is friction, still work done is 0. Tank wall is frictional, but this tank wall is frictional. I didn't get your question, Pooja. Like, look here, the molecules do not move along the walls, okay, they just collide with the walls. Understood? Friction is generally when, let us suppose if this case here, if there is some friction, then that resistance is also counted generally by applying some mu n and all these things, mu n by surface area, whatever. Now if you see, the molecules in general, they do not move along the walls, okay, they just collide with some walls at some location and they get repelled actually, okay. That's why this tank walls, you know, the tank walls friction is not of importance. Clear? Because the gas molecules don't slide over this what do you say, container walls actually. They'll just collide at one point and they come back. Understood? Now, so this is energy in minus energy out is equal to delta U for this complete system, for this tank. If you apply, then is there any energy input and energy output? Look, this is insulated system, so there is no heat interactions first of all, and this is a rigid tank, okay. So whenever this tank is a rigid tank, then definitely there is no boundary work also that's happening. So practically when you remove this partition, you can see inside this system, if you take the complete tank as the system, then there is no heat interactions or work interactions that are taking place. So therefore this energy in and energy out, both these guys are 0. So this implies delta U is equal to 0 in this case, okay. So this is the case of a free expansion, and in case of free expansions, clearly you can see there is no energy interaction, energy in and energy out. So therefore this delta U is actually 0 in this case, okay. So change in internal energy is non-zero is the wrong answer. It is actually 0, so that's why this option is wrong. Now final temperature is 50 degrees Celsius to 50 degrees Celsius, means basically they are telling you the final temperature will also remain same, okay. So this will remain same actually, is it? So let us see why it remains same, because delta U is equal to 0 and this is ideal gas. For ideal gas, delta U is equal to mass into CV times of delta T. So during this case delta U is 0, so this implies delta T is also 0. This implies final temperature is equal to initial temperature actually, okay. So in case of free expansions, the final and initial temperatures will be same because the change in internal energy is actually 0. But corresponding to the change in volume, there will be change in pressure, but the temperature initially and finally will be same because of our first law analysis. So TF is equal to Ti actually here, okay. So TF is equal to Ti. So therefore initially it is given how much, 50 degrees. So finally also this will be 50 degrees Celsius, okay. So this is correct. So option C is also correct actually. Then final pressure is 400 kilopascals. So obviously this T final is equal to T initial. So if you apply initial and final states, initially P initial V initial is equal to mass R times T initial, and finally when the gas expands completely, P final V final is equal to mass is same, total amount of mass what we are dealing is same, R times of T final actually here, okay. So if you divide these two equations, for example, so if you divide these two equations, then in that case what you can observe, this MR and MR gets cancelled. V final is 2 times of V initial, yes or no? Because you can see V final is 2 times of V initial, because they told these two are equal partitions. Whenever you remove the piston, whenever you remove the partition, this gas completely occupies the complete tank actually, okay. So the total volume occupied by the gas will be 2V. That's why VF is equal to 2 times of V initial. So if you cancel out this, this is 2, and just now we have identified the final and initial temperatures will be same actually. So this implies your P final is equal to P initial by 2 actually. Okay, so this is what you have, and P initial, they have given you some value. So what is the P initial value? P initial is 800 kilopascals, so 800 divided by 2, so 800 divided by 2, so this gives you 400 kilopascals actually. Okay, so P final is equal to 400 kilopascals is what you have clearly. Okay, so that's how you can decide the things. T initial and T final last time, this is one very important understanding. During case of free expansions, when there is no energy interaction from the surroundings, the temperature remains the same actually. Okay, because this is an ideal gas. Okay, so if it is not an ideal gas, you are not supposed to write this, but as long as the system is ideal gas, then definitely P final is equal to basically this relations can hold good, and T final is equal to T initial, and delta U is equal to 0 in this case. Clear? So definitely this final pressure is 400 kilopascals to 400 kilopascals is correct answer. So option D is also correct answer. Option A, C, D are the correct answers in this case. B is not correct because this change in internal energy is actually 0. Okay, it is written non-zero, so that's why this option is wrong actually. Clear? So please type in the chat box, is this clear to all of you? Okay, a very simple question, but you see very less bit of mathematics, only a bit of thermodynamical point of view understanding, that's it. Okay, so generally this is called the free expansion case, so I thought of putting one question here. So we'll discuss about free expansions. Okay, so free expansion, work interaction is 0, then first law if you apply, delta U is actually 0 in this case, and since the system is given to be ideal gas, TF is equal to TI. First of all, understanding this work interaction in free expansion is 0. Why it is 0 is very important, because when the gas is trying to expand, there won't be any external resistance on the right side actually. Clear? So if the tank wall is not insulated, then still work done will be 0. Yes, work done will be 0 even if it's not insulated, because the tank is rigid, so that's why there won't be any boundary work. Understood? Let us suppose if I'm keeping some paddle wheel or something, then there is again some work interactions, but if you talk about displacement work, then this displacement work is 0 because the tank walls is rigid, means the boundaries are fixed, boundary do not expand actually. Okay, clear, Pooja? So basically this tank is rigid, so that's why even though the expansion takes place, the container walls, they do not move actually. Okay, so there won't be any work interaction with the surroundings. Okay, then in that case, depending upon the some, if it is not insulated, maybe some heat transfers might be there, but that's not given in this case anyhow, so generally we do this. Fine, so let us go for this question. Piston cylinder device initially contains monoatomic perfect gas. So let us write perfect gas is there in piston cylinder, and this is monoatomic. So what is the meaning of monoatomic? Gamma is 5/3, 1.667 whatever. So this initially contains perfect gas at 150 kilopascals. So P1 150 kilopascals is the P1, and T1 is 20 degrees Celsius, which is 293 Kelvin, and 0.5 meter cube. So V1 is equal to 0.5 meter cube actually here. If the gas is compressed in a polytropic process, PV power n is equal to constant. PV power n is equal to constant to 400 kilopascals. So what about P2? P2 is 400 kilopascals and 140 degrees Celsius. So T2 is 140 degrees Celsius. So 140 is 273 and 140, this gives you 413, correct? So 413 Kelvin actually here. Okay, so 413 Kelvin. So now let us see the magnitude of the heat loss during this process is dash kilojoules. Okay, so they are asking you directly the magnitude of heat loss. So we know P1, V1, we know P2, we don't know what is V2 first of all. Okay, fine. So we don't know what is V2. So if you know V2, everything can be done. Gamma is known, N is also not known to you. Okay, you have to calculate N. So how do you calculate N? Okay, pressures and temperatures are given. So first of all, for polytropic process, let us calculate the polytropic index. Okay, so for polytropic process, we know P power 1 minus N into T power N is equal to constant, correct? So PV power N equal to constant for ideal gas, of course. So for ideal gas, they have given you, this is actually contains monoatomic perfect gas is given, So now if you see for this polytopic process, at any state p power 1 minus n into t power n is equal to constant actually. So this implies p1 power 1 minus n into t1 power n is equal to p2 power 1 minus n into t2 power n. So we need the value of this n actually. Okay, so how do you calculate this? Apply log on both sides. So if you apply log on both sides, 1 minus n times of log p1. Similarly here on the right hand side it will be 1 minus n times of ln p2. So if it comes to the left hand side, so ln p1 by p2 is equal to n times of ln t2. Similarly this n times of ln t1 from left hand side if it comes to the right hand side, so n times of ln t1 is what you have. So if you simplify this, 1 minus 1 by n minus 1, if you bring this n to the left hand side, 1 by n minus 1 is equal to ln t2 by t1 by ln p1 by p2 actually here. So if you simplify this, 1 by n minus 1 is equal to ln t2 by t1. So what about t2 by t1 actually? T2 is 413, t1 is 293. So 413 by 293 divided with ln p1 by p2. So what about p1 by p2? 150 and 400. 150 and 400. So from this you can calculate the value of the polytopic index actually. Okay, so value of n can be calculated like this from this equation. Okay, so value of n can be calculated. Now if you calculate this value of n, okay, so if you calculate this value of n, actually let us calculate ln 413 by 293. So 413 by 293 ln of this value 0.343 divided with ln 150 by 400. Okay, so divided with 150 by 400 ln. Okay, so this value minus 0.35 almost. So 1 by n minus 1 is equal to minus 0.35. So 1 by n is equal to this value plus 1 actually. So 0.65 around. So 1 by n is 0.65. So n is reciprocal of this 1.5384. 1.5384 actually here. Okay, so it is n value is in between 1 and gamma because this is monoatomic gas. So this value is 1.667, but this value is 1.5384. So n value is lying in between 1 and gamma in this case. Okay, now if you want to calculate the heat interaction, magnitude of the heat loss, so since you want this heat loss magnitude, we know Q12 is equal to gamma minus n upon gamma minus 1. So you know what is the gamma, you also calculated what is n actually, multiplied with P1 V1 minus P2 V2 by n minus 1. So here out of these things we have P1, we have V1, we know what is P2, we don't know what is V2 actually. Okay, so how do you calculate? P1 V1 power n is equal to P2 V2 power n actually. So this implies V2 is equal to V1 times of P1 by P2 whole power 1 by n actually in this case. So V2 is equal to some meter cube from this calculation. So let us see how to calculate this. P1 by P2. So what is the value of P1 by P2? 150 by 400. So if you see, let us store this value of n. So 150 by 400. So this value is 0.375. Then P1 by P2 whole power 1 by n. So whole power 1 by n actually. Okay, so 1 by n. So 0.5285. So 0.5285 into V1. So what about V1 actually? So V1 is 0.5. So if you multiply with this is 0.5. So this gives you 0.2643 around 0.2643 meter cube. 0.2643 meter cube, correct? So this is the polytopic expansion. So 0.2643 meter cube actually. Now you got the value of V2. So let us substitute. This implies magnitude of heat interaction is equal to magnitude of gamma minus n. So 5 by 3 minus this n value 1 point something 5384 by 5 by 3 minus 1 gamma minus 1 multiplied with P1 V1. So P1 is 150 kilopascals into V1 is 0.5 minus P2 V2. So what about V2 actually here? 0.2643 0.2643 by we need n minus 1. Okay, so n minus 1. So that's it. This magnitude is what we need actually here. Okay, so that magnitude, so this value in some kilojoules, this is in kilojoules because this is in kilopascals, so you have to compute this value, so you will get the correct answer. So please do the calculation. So let us see, we have calculated V2, right? So V2 into 400, this is V2 into 400. Now subtract this from 150 into 0.5, so 150 into 0.5, 75 of course. So this minus 30.71 divided with n minus 1, so divided with this value divided with n minus 1 actually. Okay, so minus 57.04 multiplied with, this is 2 by 3, this is 5 by 3 minus the polytopic value, so this multiplied with 5 by 3 minus this n, so this value, now this has to be divided with 5 by 3 minus 1, which is 2 by 3, so divided with 2 by 3 actually here, so multiplication is 1.5, so minus 10.974, so magnitude, so 10.974 kilojoules of amount of heat is being transferred in this process. Okay, so therefore magnitude of heat interaction is equal to, so how many decimal places they have asked here, so round off to 2 decimal places and take R is equal to 2 kilojoule per kg, 2 kilojoule per kg Kelvin, but here we did not get any utility to calculate R. Why R is given? Maybe to calculate the polytopic specific heat they might have given this, but anyway we need not use R in this case anyway, because we have converted the formulas in terms of pressure versus volume. We are not bothered about the temperatures. Okay, so Q122 is equal to, magnitude is 10.97 kilojoules actually here, so this is what we can do. Okay, so 10.97 kilojoules is the correct answer in this case. Okay, look how we actually you can understand this is, look, temperature difference is known to you. Okay, so maybe this R might have been given in this, if you solve this problem in this way you might get this answer. Look, I'll show you why they have given you R in this case. This is the way we have solved the problem. Okay, we have calculated n, then we calculated V2 and we have calculated 10.97. This problem can also be solved as heat interaction in this polytopic process is mass times polytopic specific heat into T2 minus T1 is what you can say here, correct? So if you want magnitude of this magnitude is what you have to keep. Then mass is, initially these conditions are given, so mass can be taken from these conditions, P1 V1 by RT1, so this mass can be written as P1 V1 by RT1 can be written for mass. Polytopic specific heat, characteristic gas constant times of gamma minus n upon 1 minus n into gamma minus 1, so this is the polytopic specific heat into T2 minus T1 actually here in this case. So if you see, then this characteristic gas constant and this characteristic gas constant get cancelled, and n value, P1 is there, V1 is there, T1 is there, T2 minus T1 is also there, and gamma value is known, gamma is 5 by 3 around. So if you calculate n, that using this part, okay, so this part you have to do to calculate n. So if you calculate n is equal to 1.5384, 1 is equal to 1.5384 is what you got. Okay, after calculating. Okay, how do you calculate n? Basically using this particular procedure. If you calculate n using this procedure 1.5384, then you got all the values. If you substitute magnitude of P1, so what about P1? 150 into V1 0.5 by T1 293, because it's 30 degrees 20 degrees Celsius sound, so 293 multiplied with gamma minus n, so gamma 5 by 3 minus 1.5384 divided with 1 minus n, so 1 minus n is minus 0.5384 multiplied with gamma minus 1 is 2 by 3 into T2 minus T1. So you can see T2 minus T1, this is 140, initially it is 20, difference is 120. Okay, so the difference value is 120 degrees or Kelvin, temperature difference is same. So since we are taking only modulus, we will delete this minus sign because there is no use of that minus sign. So if you calculate, this will be in kilojoules because this pressure is in kilopascals. Okay, so if you simplify, this is 75, so 75 by 293 into this calculation into 120. So if you simplify this, 5 by 3 minus 5 by 3 minus this n value, so n value, so this is gamma minus n divided with 2 by 3 multiplied with gamma, this n minus 1 term. Okay, so if you take this term, then this is the value 0.357. So this complete bracket is 0.357. So 75 by 293 into 75 by 293 into 75 by 293 actually multiplied with 120. So if you multiply this with 120, then you can see 10.97 in this case also 10.974. So this is the amount of heat interaction in kilojoules. Okay, but of course its magnitude, it's actually negative, it's a polytropic heat rejection. Okay, so you can see 10.97 and 10.97 in this way also. Okay, but this is a bit of more formulas to remember as compared to general thing. And here you can understand one thing, you can easily sense the heat transfer is going to be negative. Why? Because it is heat rejection. How do you know that? You can clearly see n is 1.5 384. So gamma value is 1.667 because it is 5 by 3. So 1.67 or 1.667. So clearly you can understand 1 is in between, this n value, polytropic index is in between 1 and gamma. Now if this is in the case, C polytropic is negative, but delta T is given positive in this question, correct? Because initially the temperature is 20, final temperature is 140 degrees Celsius. So there is increase in the temperature. So if temperature is increasing, then T2 minus T1 is going to be positive, but C poly is negative because of this understanding. So therefore Q polytropic, therefore heat interaction is going to be negative. This is what you can understand actually. And seriously, if you calculate, because of this minus sign, you might have got a negative value, but since we are taking magnitudes, we have deleted this minus sign and calculated the magnitude simply. Okay, so these are two different ways to solve this question, but this calculation of n is common in both the cases. Okay, so since I have calculated here already using this, then maybe this process, or you can calculate using this equation. Both are same actually. Okay, same answer comes out in both the cases. Clear to all of you? Okay, so please type in the chat box. Is this problem clear to all of you? They have given you one process from initial states and final states. They are asking you to calculate this heat transfer, magnitude of the heat transfer in that process, and this is the way how to calculate n actually. Okay, so whenever you want to calculate n, just apply logarithm on both sides of the properties which are known, and then single equation, single unknown, you can solve this equation, okay, with the help of logarithms. Clear? Now let us solve this. So this is another way to solve that question. So let us solve this question. MSQ: 55 liters of a perfect gas at 125 kilopascals and 300 Kelvin is compressed isentropically. Okay, so right now you don't know what is isentropic, so let us write, instead of this word, let us write irreversibly and adiabatically. Irreversibly and adiabatically. Okay, so let us write this word irreversibly and adiabatically, because that irreversible adiabatic process is actually isentropic. We will see when we talk about entropy. Okay, so for now let us make it irreversible and adiabatic to a temperature of 380 Kelvin. The work done on the perfect gas is 5.1 kilojoules. Take characteristic gas constant as 260 joule per kg Kelvin. Which one or more of the following statements is correct? Specified constant volume, specified constant pressure, volume at the end of the compression is dash. Okay, so out of this, so let us check this question. So 55 liters of a perfect gas initially, V1 is equal to 55 liters. So if you convert this 55 liters, 55 into 1 liter is equal to 10 power minus 3 meter cube. So 10 power minus 3 meter cube. So this is 0.055 meter cube actually. Okay, do you know this conversion, liters to meter cube? Because you all might have studied this. 1 liter is equal to 1000 cc, centimeter cube. Okay, so 1 centimeter is equal to 10 power minus 2 meters whole cube, because this is centimeter cube. So if you simplify, 10 cube into 10 power minus 6 meter cube, so the net effect of these two is 10 power minus 3. That's why 1 liter is equal to 110 power minus 3 meter cube. Therefore 55 liters is equal to 55 into 10 power minus 3 meter cube here. Okay, so that's why we are writing 0.055 meter cube. Now if you see 55 liters of perfect gas at 125 kilopascals, so P1 is 125 kilopascals and temperature T1 is 300 Kelvin. T1 is 300 Kelvin actually. is compressed reversibly and adiabatically. So the process that we are following is PV power gamma is equal to constant because it's adiabatic. Temperature of is compressed to a temperature of 380 Kelvin. So T2 380 Kelvin actually. Okay, so 380 Kelvin. The work done on perfect gas is 5.1 kilojoules. So the work interaction in the perfect gas is 5.1 kilojoules. Obviously this is negative because we are actually doing compression. Okay, so this magnitude is 5.1 kilojoules. So W122 is minus 5.1 kilojoules actually because it is compression. So you are actually doing work on the system. Okay, so following the classical sign convention, minus 5.1 kilojoules is what you have. Okay, so take characteristic gas constant R is equal to 260 joule per kg Kelvin. So characteristic gas constant is equal to 0.26 kilojoule per kg Kelvin. 260 joules or 0.26 kilojoule per kg Kelvin, both are same. Then so we identified these things. Which one or more of the following statements is correct? Specific heat at constant volume, specific heat at constant pressure actually. Okay, so first of all, how do we calculate this specific heat at constant volume? First of all, CV is nothing but R upon gamma minus 1. Okay, but here what we have to identify, we don't know what is the value of gamma, correct? Gamma is not known because they have just given perfect gas. You can calculate gamma. How can you calculate this? V1 is known, work interaction is also given, correct? So work interaction is known, so we'll do one thing. This work interaction is equal to P1 V1 minus P2 V2 upon gamma minus 1 because n minus 1 generally, so n is equal to gamma in this case, so gamma minus 1, but we don't know what is V2 actually. Okay, so V2 is also not known to you still. We know only about this R and also the work interaction P1, T1 and T2. Okay, so we don't know what is gamma actually. Characteristic gas constant is known to you, so gamma, we have to calculate gamma. So how do you calculate this gamma? So T1 is known, T2 is known, P1 is also known, correct? Is this a rigid container? No, 55 liters of a perfect gas is contained, 380 Kelvin. Work done on the perfect gas is 5.1 kilojoules. We have to calculate this. CV is equal to this R by gamma minus 1. They have given in kilojoule per kg, joule per kg Kelvin. Okay, fine. So we need to calculate gamma somehow. How we can calculate the gamma? Pressure, volume and temperature are given. So P, T, V is given. So you know the mass. So if you know mass, then what we can do? PV power gamma is equal to constant. We have to calculate this value of gamma. Any idea how we can calculate the gamma? Because V2 is not known, but temperatures is known, correct? So we'll do one thing. If you take P1 V1 out, because P1 and V1 is known to you, minus 5.1 is equal to P1 V1. If you take out 1 minus P2 V2 by P1 V1 by gamma minus 1. So one thing that we can know is this P2 V2 by P1 V1 is nothing but T2 by T1 actually. This term is going to be T2 by T1 because this is MRT2, this is MRT1. Okay, yes, mass can be calculated from initial MRDT by gamma minus 1. Yes, exactly. So if you take P1 V1 out, this term is going to be T2 by T1 and we know T2 and we also know T1, correct? So let us suppose if we simplify this, minus 5.1 is equal to P1 V1. So what about P1 V1 actually in this case? P1 V1, P1 is 125 kilopascals into V1 is 0.055 by gamma minus 1 by gamma minus 1 actually multiplied with 1 minus T2 by T1. So T2 is 380 and this is 300 actually. So this value is more than 1 and because of which this minus sign, because it's a compression obviously, so work interaction is negative. So single equation, single unknown, we can calculate gamma. So from this, let us calculate what is the value of gamma in this case. So let us calculate gamma. So let us, gamma minus 1 is equal to, of course, if you, let us see, 1 minus 38 by 30, 1 minus 38 by 30, 380 by 300, so 38 by 30 minus 0.26 and deleting this minus sign, neglect the minus sign there also. Okay, so fine. Then multiplied with 125 into 0.055, multiplied with 125 into 0.055. So this value divided with 5.1. So divided with 5.1 actually here. So 0.359, this is actually gamma minus 1. So gamma minus 1 is equal to 0.359. So gamma is equal to plus 1. Add to 1 to this 1.3594. 1.3594 actually here. Okay, so this is the value of gamma from this simple calculation, 1.3594 actually. So this is the value of gamma directly. Okay, now you know the gamma, so you can calculate this. So this implies CV is equal to R, characteristic gas constant is given 0.26 or 260 joules. So 260 by gamma minus 1. So gamma minus 1 is 0.3594 actually. So this, if you simplify, your answer is in joule per kg Kelvin. Okay, so this answer is going to be in joule per kg Kelvin actually, because this value of characteristic gas constant you have kept in joule per kg Kelvin. So 260 divided with, so let us store this value, 260 divided with, recall, minus 1. So 723.27, 723.27 actually, 723.27 joule per kg Kelvin. So if you check this, 1246 is given, so this is wrong actually. Okay, so this value is wrong. Specific heated constant volume is not that value. This is around 723.27. Now CP, specific heated constant pressure. So CP is equal to gamma times of R by gamma minus 1 actually. So this is nothing but gamma times of CV. So we have calculated CV already. So CP is going to be again certain joule per kg Kelvin. Joule per kg Kelvin actually. So gamma times of this value. So this value multiplied with gamma. So that gives you 983.27. 983.27 joule per kg Kelvin. Okay, so 983. Yes, this is coming, gamma is coming out to be 1.36, correct Balaji, and this is 723.27 exactly. Okay, but since here this is given 1200 around, so that is actually wrong. Now coming to this 978 to 986, and this is 983. So 983 is in between these two values. So definitely this is actually correct. So this statement is correct. Option B is correct actually. Volume at the end of the compression is dash 31 to 34, 27 to 30. So let us calculate this volume at the end of the compression. So since we got the value of gamma, we know P1, but temperatures are known to you. So fine. T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1. So this implies V2 is equal to V1 times of T1 by T2 whole power 1 upon gamma minus 1 actually. So if you simplify this, this answer is going to be in some meter cube. So how do you calculate this? T1 by T2. So T1 by T2, T1 by T2 whole power 1 by gamma minus 1. So we collect minus 1 actually here. Okay, so if you simplify 0.518 multiplied with V1. So V1 is 0.055. Yeah, so please type in the chat box. Is it okay now? It's not buffering, correct? So please type in the chat box. Is this clear? Video is on again, right? Guys, whenever if class gets buffered, please wait for 1-2 minutes, because there are certain power taping issues with the inverter, so that's why system is getting shut down. So to restart that, it takes hardly 1 minute, so please be online. Okay, we shall continue now. So this value, final calculation is 0.0285, almost 0.0285, 0.0285 meter cube. So meter cube, if you convert to liters, again because options are given in liters, you can see options are given actually in liters. So if you convert 28.5 liters almost, correct? So V2 is equal to 28.5 liters is what you have here. Okay, so this V2 is 28.5 liters is what you have here. So this is the final volume after the compression. So if you check these options, so 27 to 30, so 28.5 is exactly in between this. So this is actually wrong and this is correct answer. So we can say option D is correct, but option C is actually wrong. Okay, so B and D are the correct answers in this case, and this is as per this calculation. Clearly you can see. Okay, so is this clear? This question is very simple. The only thing is you have to identify what is gamma. To calculate gamma, they have given you this work interaction. So once you calculate work interaction using this simple formula, then if you relate these two equations, then gamma is equal to 1.3594. Many times if you misunderstand and if you write only 5.1, then you will end up with some another negative value of gamma actually. Okay, so that should not be written actually. Clear? Now, so, and generally you should have this idea that gamma will be around 1.4, 1.67 or somewhere in between this. Okay, so when you get values like this, they are comparative, but if you get values of gamma like 0.1, 0.2, then that means your calculation is somewhere wrong. Okay, so these are some common checks and balances we can do before entering the answers, okay, in gate examination also. Like for example, you see, let us suppose after complete calculation, let us suppose they are asking, you know, characteristic gas constant of atmospheric air, for example. Okay, after solving the complete problem, your answer should be somewhere around 0.26, 0.28, 0.29, within this range. Okay, if you are getting 0.1, 0.07, these kind of answers, that means they are definitely calculation mistakes, because generally you should think physically what could be the possible value because before entering the answer directly. Okay, fine. So let us solve one question. This, I think this is the, how many questions are left? Fine, this is the last question. So let us solve this question. 1 kg air is held inside a non-insulated cylinder. Okay, there is a non-insulated cylinder, non-insulated, fine. Okay, using a piston of mass and area and stoppers. There are two stoppers of negligible area as shown in the figure. The initial pressure Pi and temperature Ti of air inside the cylinder are 200 kilopascals and 400 degrees Celsius. Yes, you can see 200 kilopascals and 400 respectively. Ambient pressure is P infinity, so P infinity is 100 kilopascals and temperature T infinity is 27 degrees Celsius respectively. Which one or more of the following statement or statements is correct actually here in this case? Okay, so let us check. I think this is a very lengthy question, so let us solve carefully. Okay, let us solve. Temperature of air inside the cylinder at which piston will begin to move. Ratio of final sorry, excuse me. Ratio of final minimum volume where the piston stops moving to the initial maximum volume where the piston starts moving is dash. Total heat rejection, temperature of air when the volume of air is 90% of its initial volume of air is dash. So let us see. First of all, this is a very nice question. Solution. So see here, 1 kg of air. So first of all, mass is equal to 1 kg. Mass is equal to 1 kg actually of air is held inside a non-insulated. So if it is non-insulated, depending upon the movement of the piston, some heat can get exchanged with the surroundings, or depending upon certain heat exchange, this piston can also have stoppers as shown in the figure. Okay, so this is the initial configuration of the figure at which the piston is at the stops and the pressure and temperature are here. The initial pressure Pi and temperature Ti of air inside the cylinder are 200 kilopascals and 400 degrees Celsius. Okay, so initially P initial is equal to, how much is this? 200 kilopascals, and you know 200 kilopascals, and what they have given initial temperature is how much? Initial temperature is 400 degrees Celsius. 400 degrees Celsius, and this piston is at the stoppers, means the piston is not able to move up, it is actually located there. The ambient pressure and temperature P infinity is 100 kilopascals, ambient is surrounding pressure is 150 kilopascals, and T infinity is equal to, so T infinity is equal to 27 degrees Celsius, which is 300 Kelvin, and this is around 673 Kelvin. Okay, 673 Kelvin, and that's 300 Kelvin. Then try to calculate this respectively. Which one of the following or more statements is or correct? Firstly guys, tell me one thing. If you take this piston cylinder assembly, let me draw once. So when you take this piston cylinder assembly, if you have this piston like this, if you have this piston like this, they told there are stoppers here. Stoppers of negligible area, They told they are of negligible area. What do they mean by negligible area? That means whatever is the area of the piston, same area we can take for the atmospheric pressure actually. Okay, so these are stoppers actually. Okay, so these are stoppers actually here. Fine, these are stoppers. Stoppers. Okay, so these are stoppers. Now there is some gas inside this. So there is some gas inside this. Now try to understand this. Initially this is at 400 degrees Celsius and 200 kilopascals, and on the top it is 100 kilopascals and ambient is at 27 degrees Celsius. So try to understand this cylinder is non-insulated. Initially try to understand one thing very carefully here. This temperature is 400 degrees Celsius. This is not insulated. Outside temperature is only 27 degrees Celsius. Outside temperature is 27 degrees Celsius. Then whenever this outside temperature is 27 degrees Celsius, because of this temperature difference, what happens? Heat will actually flow out of the system. Correct? Heat starts flowing out of the system, and eventually this temperature of the gas will start decreasing, because obviously if we keep a hot body in atmospheric air, then what happens? Heat gets transferred, right? Very common understanding. So heat starts flowing out. Good. Heat starts flowing out. Now tell me one thing. At this configuration, initially the piston is bounded by these stoppers. Let us suppose if heat starts flowing out because of this temperature difference. Let us suppose the temperature becomes 398 degrees Celsius. After some small time, what happens? Because of some heat transfer, let us suppose this temperature drops by some small amount. And obviously if temperature is dropping, then definitely pressure can also change. So immediately as soon as the heat transfer starts, will the piston start moving down? My question is, immediately as soon as some heat transfer starts, will the piston start moving down actually? Will the piston start moving down? Will the piston start moving down? As soon as the heat transfer gets started, will the piston start moving down actually? Will the piston start moving down or no? Yes or no? Yes? No. Actually, this is the main logic of this question. Okay, why? Because the piston immediately won't start moving down, because look, I'll tell you why. Look, this is a good question because of this answer. I know all of you will say yes, because your intention is that obviously when heat transfers, this piston starts moving because of the pressure drop. But the pressure drop will not be sufficient for the movement of the piston, because look, I'll tell you why it's happening. If you draw the force balance on the piston, actually, oh sorry, just a minute. There is pressure due to gas on the bottom. Okay, now on the top there is atmospheric pressure. and also there is certain weight of the piston actually. Weight of the piston. This is pressure due to the gas and this is atmospheric pressure. Now try to understand this very carefully. If this piston has to come down, definitely stoppers reaction, we will neglect the stoppers reaction, okay, because at the point of disconnecting I'm talking, okay. So at the point when slightly the piston starts moving, then the contact between the stoppers and the piston is lost. That's why I'm not taking the stoppers reaction, okay, because I want to look, my intention is to calculate the pressure at which the piston starts moving, and the piston just when it starts moving, the contact between the stoppers and the piston will be lost, okay. So that's why I'm not taking the stoppers reaction, okay Balaji. Now if you see this case, normally the pressures externally due to this atmospheric and weight of the piston will be able to move the piston only when this pressure due to the gas is less than the combined effect. Means obviously at limiting position, means at equilibrium position, when the piston is about to move, if you apply sigma Fy is equal to 0 at that equilibrium state, we know clearly that pressure due to the gas is equal to P atm plus weight of the piston by area of the piston actually. Area of the piston. So if you calculate this, your P is equal to, this is 100 kilopascals plus weight of the piston. So what about the weight of the piston? They have given 25 kgs mass and gravity is 10 meters per second square, okay. Mass of the piston is 25 kgs. So 25 kgs into 10, this is the force in newtons by area. So what about the area, cross sectional area again? So cross sectional area is 100 centimeters square. So 100 centimeters square is nothing but 10 power minus 4 meter square, okay. 1 centimeter square is 10 power minus 4 meter square. So this is weight by area. So this is in pascals, but this is in kilopascals. So if you want to convert this to kilopascals, you have to multiply a 10 power minus 3. So this term is in kilopascals, this bracketed term is also in kilopascals now. So if you simplify this 10 power and this 10 and this 10 power minus 3 cancels out this 10 power minus 4 completely, okay, and this 10 and this 10 gets cancelled. So you can understand here pressure P sorry guys, so 125 kilopascals, 125 kilopascals. So one thing you can understand here from this understanding, totally at any point the top load on the piston, means the load which is acting to push the piston, is equal to 125 kilopascals. Now if this force is capable of pushing this piston down, that means definitely this pressure inside this container, means the pressure due to the gas, should also fall to 125 kilopascals. As on means until the pressure comes from 200 to 125, this piston will not move from there, correct? Can I say this? Because the total effective load that is pushing the piston from the top is 125 kilopascals. So until the pressure of the gas comes to 125 kilopascals, the piston cannot move from that situation, okay. So the piston will be at that location, understood? So that's why to lose the pressure from 200 kilopascals to 125 kilopascals, some heat has to flow out. So that's why immediately after the heat transfer, means heat starts flowing out, the piston will not come down, okay, until the pressure drops to 125 kilopascals from 200 kilopascals, the piston will remain at that position. Clear? So this is one very important concept in this question. Clear? It's not always like immediately heat starts flowing out, the piston starts coming down. So that means from 200 kilopascals, means you can see from 200 kilopascals to 125 kilopascals, until this pressure is reached, the process that happens, means the heat rejection, what happens is at constant volume, because the piston will not move in this case, okay. So this is a constant volume process. Is this clear to all of you till this point? So please type in the chat box. So please type in the chat box. Is this point clear to all of you till this particular discussion? From 200 kilopascals until the pressure of the gas comes to 125 kilopascals, the process or the heat rejection happens at constant volume, because this piston will not move actually. The top load acting on the piston is not capable of moving that piston down till that point. Yes? Is this clear to all of you till this understanding? Everyone, so please type in the chat box. Balaji, Pooja, Yogesh, all of you. Okay, so now once this piston starts moving down, then can you tell me after the piston starts moving down, what will be the process? After the piston starts moving down, the load on the top of the piston will be constant, means at any during the movement of this piston at any equilibrium position, this is going to be the case, and that means the process is going to be a constant pressure process. Yes or no? Because at any equilibrium position in between the same analysis, if you do, we'll see the pressure of the gas is 125 kilopascals. It is constant pressure, means therefore you can see if you plot on a PV, diagram, if you plot on a PV diagram, pressure, volume. So initially it is at some volume. Initially this is at some volume. So initially the state of the gas is somewhere here 1. So from there the pressure initially drops to 125 kilopascals, maybe somewhere here. Okay, so this is 200 kilopascals. So it falls to 125 kilopascals along this constant volume process. Then it is constant pressure compression, because volume actually decreases and heat goes out. So it is a constant pressure compression up to some particular state. We don't know what is the final volume. If they give, we'll calculate, or else we'll see. So 3, this is constant pressure process. We don't know what is the state 3 still, but we know one thing. Okay, so this volume initially is not known, but characteristic gas constant is given to you. So characteristic gas constant, did they mention? Air. Okay, so they have given this substance, this is air, so gamma is equal to 1.4. so they have given you this substance is air, actually atmospheric air. So gamma is 1.4 and Cp, Cv, all the values wherever required we can use. So first of all, this is the process. So first of all, there is some constant volume process up to which the pressure falls to 125 kilopascals, and then constant pressure process. Okay, so this value at which the process shifts from constant volume to constant pressure is 125 kilopascals. Now let us talk about the things. The temperature of the air inside the cylinder at which piston will begin to move is dash. So the temperature of the air inside at which the piston begins to move. So we know that the piston begins to move at 125 kilopascals. So we know that option A, piston begins to move when P is equal to 125 kilopascals, means basically piston starts moving at this point, volume starts changing at this point, therefore we need T2. So we know 1 to 2 is constant volume process, So therefore P1 V1 is equal to mRT1 and P2 V2 is equal to mRT2 actually here. Okay, so mass into characteristic gas constant, these two gets cancelled. So volume is same, initially whatever the volume is at state 1, same will be the volume at state 2. So P1 is 200 kilopascals by 125 kilopascals is equal to T1 is, T1 is how much? 400 degrees Celsius, right? So 673 Kelvin. So this is 673 by T2. So this is what you have to calculate. So T2 is equal to some Kelvin again. And what are the options given in? So this is given in degrees Celsius. So if you can calculate in Kelvin, this can be written in degrees Celsius easily. Okay, so this is how we can calculate the T2 at the temperature at which the piston starts moving. Okay, so if you simplify this value, 673 into 125 by 200. Sorry, excuse me guys, I'm having cold, so that's why I'm sneezing, so sorry for that. So 673 into 125 by 200, 673 into 125 by 200, so 420.625 Kelvin. So 420.625 Kelvin. So minus 273. So this gives you 147.6. 0.6 degrees Celsius. So this is the temperature at which the heat starts, 147.6 degrees Celsius is the temperature at which the piston starts moving. So if you check the options, 147.6, 140.76 is in between exactly this. So this is actually the correct statement. Okay, so this statement is correct. Option A is correct because the temperature of the air at which the piston starts moving down is 147. Yes, 147.65. That's what even we got, 147.625 degrees Celsius. Now, the ratio of the final minimum volume when the piston stops moving. So basically, look, one thing that we can understand is the piston will not continuously touch the bottom of the piston starts moving down, then it won't touch the bottom of the cylinder, correct? At some point when it reaches, due to further heat transfer, the temperature will drop from 147 degrees Celsius to 27 degrees Celsius at some point. So whenever there is thermal equilibrium between system and the surroundings, then definitely the compression will stop at that point, means the heat transfer will stop because the temperature difference will not be there. So therefore, after 27 degrees Celsius, initially the piston starts moving at 147.6 degrees Celsius around. So from there it comes to around some 120, 27 degrees Celsius and it stops. Means basically in this case, this stops when T3 is equal to 27 degrees Celsius, which is 300 Kelvin. 300 Kelvin actually here. Okay, so 300 Kelvin. Now, let us see this case. What they are asking, the ratio of final minimum volume, means basically this is the final minimum volume V3 to the initial maximum volume, so which is nothing but V1. So V3 by V1 is what they are asking. Option B, V3 by V1. So this can be written as V3 by V2 because 1 to 2 is constant volume process and this is happening at constant pressure. So 2 to 3 is constant pressure process. Constant pressure process. So if this is constant pressure process, then we know this implies V3 by V2 is equal to T3 by T2. So T3, the expansion will stop when the compression will stop when T3 is equal to 27 degrees Celsius, which is 300 Kelvin, by T2 is this, which is 420.62, 420.625 Kelvin actually. Okay, so this is the ratio. So V3 by V1, which is V3 by V2, is same as this ratio. So this is dimensionless, of course. So 300 by 420.625. So this reciprocated multiplied with 300. So if you see 0.713, 0.713. 0.713 actually, correct? You all got 0.713. So 0.713. So if you see, this is 0.71. 0.71 is in between this 0.68 and 0.674. So definitely this is also the correct statement. So therefore option B is also correct answer in this case. Okay, because you can see clearly V3 by V1 is 0.713. Next, what is the quantity that is needed? The total heat rejection. The total heat rejection when piston stops moving is dash. So what is the total amount of heat rejection actually? So if you see, Q123 is equal to heat interaction in the process 1 to 2 plus heat interaction in the process 2 to 3. Now if you see, for process 1 to 2, Q12 is equal to Q12 minus W12 is equal to delta U actually here. Okay, and this is 0 because it's a constant volume process, so there is no work interaction. So this can be written as U2 minus U1 plus, this is a constant pressure process. We have seen in case of constant pressure process, the heat interaction is nothing but change in enthalpy. We have seen in yesterday's class. At constant pressure process, heat interaction is equal to the enthalpy change. So H3 minus H2 actually, and this is ideal gas. So we can see U2 minus U1 is mass into specific heat at constant volume into T2 minus T1 plus mass into, this is again ideal gas, so specific heat at constant pressure into T3 minus T2. Now here we don't know what is mass actually. How do we calculate the mass actually? Mass is given 1 kg directly. Okay, so mass is given, it's 1 kg directly. So you can see this is 1, this is also 1. CV for air, we have given the values. CV of air is 0.718 kilojoule per kg Kelvin, and Cp of air is 1.005 kilojoule per kg Kelvin actually. Now these are compressions anyhow. So CV 0.718 times of T2 minus T1. So T2 is 420.625 minus T1 is 673 plus Cp. So Cp is 1.005 multiplied with T3 300 Kelvin minus T2 which is 420.625. 420.625 actually. Okay, so if you simplify this answer is going to be negative, of course, because these two are negative terms. So kilojoules, because we have kept the CPCV values in kilojoule per kg Kelvin. So if you simplify, the answer is going to be in kilojoules. The options are also given in kilojoules. Okay, so let us calculate that value. So calculate this value, 420.625 sorry 420.625 minus 673. Okay, so this value multiplied with 0.718 plus 300 minus 420, so minus 120.625 multiplied with 1.005 actually. Okay, so 1 multiplied with 1.005, so minus 302.43 minus 302.43 kilojoules actually here. So minus 302.43 kilojoules is the total amount of heat interaction in this process. So minus 302 it should be there. So minus 306 through minus 300, so minus 302 is in between again. Okay, so this option is also correct in this case. So option C is correct answer, because you can see total heat interaction in this case when piston stops moving means starting to final. So minus 306.45 kilojoules to minus 300.45 kilojoules actually. So this statement is also correct. Now let us see what is the last statement. The temperature of air when volume of air is 90% of its initial volume. Okay, so basically if you see what happens during this constant pressure process, this is the initial volume, or this both are same. So when piston starts moving, the volume of the gas initially, the volume of the gas eventually decreases. Okay, so therefore at this point if you see 90% of its initial volume, so let us suppose if this is V1, this is somewhere here 90% of V1. So what is the temperature at that state? So let us suppose this is state 4 for example, then they are asking you T4. Now you know basically this process 2 to 4 is actually constant pressure process. So we know that V2 by V4 is equal to T2 by T4, because 2 to 4 is constant pressure process actually. Okay, so 2 to 4 is constant pressure process. So T2 is known, V2 is also known. So V2 by V4 is 90% of the volume. So 0.9 times of V2 is equal to T2. So what about T2? 420.625 by T4 actually. Okay, so this gives you the calculation of T4 in some Kelvin, and finally I think they want in degrees Celsius. Options are in degrees Celsius actually here. Okay, so they have given in degrees Celsius. So let us calculate this. So anyhow here if you see this V2 and V2 gets cancelled. So 420.625 multiplied with 0.9 is T4 actually. Okay, so 420.625 multiplied with 0.9, so this gives you 378.56 378.56 Kelvin. Okay, so 378.56 Kelvin. So this has to be subtracted with 273, so minus 273, so this gives you 105.56 105.56 degrees Celsius actually here. Okay, so 105.56 degrees Celsius. So 105.56, you see 105.57 is in between this, so this is also correct option. So this is a option with all 4 correct options actually. So this is a one very important and very beautiful question actually, because you see we have used a lot of concepts here. Understood? Initially the main idea that the main intuition is that whenever heat starts flowing out, the piston will start dropping, but this need not happen always, because the pressure of 125 kilopascals is just sufficient to hold the piston till the stoppers. So from 200 kilopascals to 125 kilopascals, the piston will stay at that particular position. Okay, so that's why the PV diagram is as per this 1 to 2 and 2 to 3 is constant pressure process actually. Okay, so clear to all of you? So this is a very nice question actually. We have used a lot of understanding of thermodynamics in this. Okay, fine, clear. I hope it is a simple question actually. I mean, like, very important question, but of course you see it's not complicated, but you have to understand the things a bit carefully. That's it. Okay. Others, all of you, please type in the chat box. Whoever is on live, everyone should please type in the chat box. I think this is the last question. We'll start open system analysis. Okay, yeah, we'll start open system analysis. So till here, till this heat interactions, I hope is everything clear to you. Okay, now so let us start this open system analysis. So introduction to open systems basically. So open system, we have seen what is an open system. Basically the system in which both mass and energy transactions can take place. Okay, so we will discuss about this open systems, and you will see in terms of all the formulas, if you put the mass terms 0, you will get the formulas for closed system analysis again. Okay, so anyway, we will see that. So first of all, we have seen what is an open system. So this is a system so this is boundary, and obviously you have some surroundings. Then across the system we have mass interactions. Mass interactions are permitted, and also energy interactions are permitted. These are also permitted actually. Okay, so these are also called control volumes, because we have seen when we are defining the systems, a quantity of matter or region in space actually which is under study is called a system. So in this case we cannot focus on mass, because mass continuously flows in and flows out. So therefore we focus on this volume. Like for example, you take a turbine. Okay, so your point of interest is always what's happening inside the turbine, but not about the mass going into the turbine and leaving out actually. Okay, so inside the turbine, what's happening to this mass, how the properties are changing, how some work is getting generated. So your focus is always on the turbine part. Okay, so that's why these are also called as since the focus is on some volumes, this open systems are also called as control volumes actually. Okay, so that's why open system analysis is also sometimes called as analysis of control volumes. Okay, so this system, open systems, open system is also called a control volume. Is also called a control volume actually, and this is also called as control volume analysis. Now if you see energy of a system in a control volume, okay, so normally we have seen in case of closed systems, for closed systems where basically if you talk about the energy of the system, we have seen the energy is equal to macroscopic kinetic energy plus macroscopic potential energy plus internal energy of the system actually. Okay, so plus internal energy of the system. Now when you take this control mass, for example, so these are the examples, these are the types of energies that we have: macroscopic kinetic, macroscopic potential, and internal energy. But when you talk about this case of open systems, let us see what happens. If you take the case of open system, so let us suppose if there is some, for open systems or control volumes, so let us see what happens. Let us suppose if you take a control volume, for example like this, where it has some inlet and it also has got some outlet. Okay, so Fine. Okay. Now if you take this boundary of the control volume, okay, so let us suppose this is your control volume in this case. Control volume, so some space in the turbine, so some space. Now when I write energy of the control volume, energy of control volume, this means initially if you take this empty tank, means if you take only this space, that space do not have any energy actually, okay, but at any instant what happens, there will be some mass inside this control volume, okay. So what is the energy corresponding to that mass is what we will declare as the energy of the control volume, okay, because if you take an empty turbine, then let us suppose if the turbine is not operating, it is at empty, it is ideal, okay. So let us suppose if there is some simple turbine which is not running, then in that case what happens, definitely we cannot say something like energy of the control volume because there is no mass inside. But whenever the turbine is operational, then there is some mass which is flowing in, some air or something, some substance is flowing in. So at any particular point there is always some mass inside the control volume. So mass inside the control volume is mcv at any instant. Mass inside the control volume, mass inside the control volume, and when you are writing energy of the control volume, this is nothing but energy of mass inside the control volume, inside the control volume at any instant, at any instant actually here, okay. So energy of mass inside the control volume at any instant. Now try to understand one thing very importantly. Look, if you take this as control volume, then definitely there is some inlet for the control volume and outlet for the control volume, correct. Now let us suppose if the control volume is at some elevation, also there is some elevation difference. For example, you take this reference somewhere here, let us suppose with respect to ground you are talking, then this elevation with respect to ground you can say Z1, and let us say this elevation with respect to ground here, this is Z2 to that point. Means inlet and outlet are at some elevation difference in general. Let us suppose if they maintain some elevation difference, then with respect to some reference there is difference between this elevation at inlet and elevation at outlet. And also let us suppose if the fluid is flowing in this direction, so there is some motion of the fluid, not exactly like this, but it enters and then it leaves, that's what I mean. Inside, depending upon the turbine, pump or nozzle, depending upon the type of the volume, the direction of the motion and all are designed. Now try to tell me one thing, whenever you take this particular position, whenever the fluid is entering this control volume, means at this boundary where mass is actually flowing in and here where the mass is actually flowing out. Tell me one thing, here at the point of exit, at the point of entry, what's happening, complete fluid is moving in a particular direction, means can I say there is bulk motion of this fluid, yes or no? At the inlet if you see complete fluid, let us suppose if you connect a pipe to a boiler, then what happens, fluid flows through the pipe in a particular direction actually, yes or no? So fluid flows into the pipeline, fluid flows through the pipeline into the boiler or turbine, wherever, to some particular tube, and inside the tube there is some bulk motion of a fluid in a particular direction, correct? Can I say this? There is some bulk motion of the fluid in a particular direction actually. So whenever there is a bulk motion of the fluid in a particular direction, then what happens here, this kinetic energy, there is some macroscopic kinetic energy that is available for the system, and as soon as the system is entering, depending upon the functionality, depending upon if there is some turbine, if there is some rotor, things like that, the fluid which is crossing this boundary, which is entering into this control volume, will have energy which is equivalent to this control, this kinetic energy actually. Similarly here, the energy which is leaving out will also have some kinetic energy. Okay, so means basically whenever you talk about this mass which has entered this control volume, let us suppose there is some mass which is entering this control volume. This mass, when it is coming inside, it has some energy which is equal to the kinetic energy of the fluid because of the bulk motion actually here. So that's why this mass of the control volume or energy of the control volume is equal to kinetic energy macroscopic, which is at the entry and also at the exit. Okay, so basically if you talk about the control volume, then whatever is there at the inlet, so that is there at this particular point, plus this fluid is also coming at some elevation. So with respect to some reference, some ground level or something, let us suppose if a plane is flying, then definitely what happens, the potential head is there. Okay, so therefore this potential head is also there actually. So that's why with respect to potential head, there is some potential energy of this fluid, and this potential energy of the fluid is also carried inside. Okay, so therefore this potential energy of the fluid is also carried, and depending upon the type of fluid, its temperature and all, the fluid always has some internal energy, whether it's flowing or non-flowing, definitely we have some internal energy. Plus now these three things we have also seen here, kinetic energy plus potential energy plus internal energy. Now there is one last form of energy which is also present in the fluid actually. So what is that energy? Okay, so we have something called flow energy. I told you in third chapters, I mean in the heat interactions chapter, I told you that I'll give you about this enthalpy in a much broader sense. So you can see here flow energy. So what is this flow energy? Okay, first they are very clear, because the fluid is having some bulk motion, this kinetic energy gets stored in this mass as some form of energy, which is we'll writing as kinetic energy. Similarly, due to this potential head, there is some energy which is getting stored inside, so that's called the potential energy, and because of the chemical nature and temperature everything, the system has got some internal energy. So there is U. Now what is this flow energy, which is one very important concept in case of this open systems. Okay, so let us see what is this flow energy. So let us see what is this flow energy actually. Let us suppose if we take this control volume. Okay, so if you take this control volume, okay, so now if you take this control volume like this, okay, so this is the boundary of course. Then this is the control volume, and this control volume has some mass of the control volume and the fluid. Now whenever the fluid is flowing, look, this kinetic, potential, internal energies are very clear. Now what is this flow energy actually? Okay, so we have to understand that in a just a minute. Okay, nothing, streaming is going fine, right? No issues with the class. Okay, no internet issue, no? It's going okay. So let us see. So what we are talking, okay, flow energy. So this is boundary. So here if you see, whenever this flow is happening in this direction, if you look at this in a broader sense actually, see what happens. If you look at this in a large scale, So for example, if you look at this region, if you see this region in a large scale actually, there is some fluid which is flowing. Now try to understand one thing here. Let us suppose at this section in the flow, inlet to the pipe, or this is the inlet pipe or something. So let us suppose at this section, if the pressure is P, for example, if the pressure is P actually, if you look at this motion of fluid at some larger sense, okay, at some microscopic sense, if you look at the motion of the fluid, then you will understand that this fluid can be idealized or visualized as some blocks actually. So this can be idealized as a block. Similarly, this is second block, third block of fluid, fourth block of fluid actually. Now, so this is how we have the blocks. Now tell me one thing, if the flow has to maintain, okay, means if this fluid has to cross this control volume, means if it has to cross the boundary, means if flow has to maintain, how the flow gets maintained actually? That's because this block which is actually to the left of the first block will actually push this block into the control volume actually, okay. Similarly, this third block which is here will push this second block. Similarly, this fourth block will push this third block actually. So like this, let us suppose in a movie counter line, for example, if you see how every individual pushes the previous person, similarly to maintain this flow into the control volume, what happens is like every block of the fluid will push the preceding blocks and these blocks will fall into the control volume actually. Similarly, when it comes here the fluid blocks which are here will actually push the fluid out, so that's how the outward flow is maintained. Means every successive block of the fluid will try to push its preceding block both at the inlet and also exit, okay. So whenever this block is pushing, let us suppose here if the pressure is P at this point, so let us suppose at this point if the pressure is P, for example, then if this is P and the area of cross section is A, for example, and let us suppose if this is pushing by some amount dx actually here in this case, okay. So let us suppose x, if you write x, some length up to which it is pushing. So let us suppose if this is P, Ax. Now try to understand this. There is a fluid block at this situation. There is also one more fluid block at this point. Now what's happening, this block, second block, is pushing this first block, okay. So what is the pressure at which it is pushing this? So the pressure at which this is pushing is basically equal to P, because at this interface the pressure is P. That means at every point on this fluid, 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 let us suppose if this is P, at every point on this fluid, if you see this is the first block actually, first block of fluid, okay. So this is the first block of fluid, then you can understand there is a pressure which is equal to P that is acting at every point here. A pressure which is equal to P is acting here, correct. So this pressure P is actually pushing the block. Now whenever it is pushing the block instantaneously, let us suppose I am talking about instantaneously. So let us suppose this pressure is P for a small change dx, for example, okay. So let us take this dx because pressure continuously changes generally during the flow. So let us take dx, okay. So they have moved a small distance dx actually. Now definitely the second block of the fluid has done some work on the first block of the fluid in moving this into the control volume. So what is the work done actually here, okay. So work done is equal to pressure into, let us suppose if this area is A, which is the cross section of the pipe generally. So let us suppose if the area is A, then P into A times of dx. So the instantaneous work which is done at that case is equal to P times of dV, and generally this dx and area depends upon the cross sections of the pipe and all. So if you want to write in terms of intensive properties, the specific work done can be written as P into the specific volume at that instant, correct? Because within dV, during this small distance, the volume doesn't change much. So let us suppose if we take a constant, some small finite value of x, we can say W is equal to P into V actually here, okay? Because we generally write the things in intensive properties, because this capital A, this dx, these guys can change depending upon the length of the pipe, cross section of the pipe and all these things. But if you write in terms of properties, so P into the specific volume of the fluid is the amount of work which is done by the second block on the first block to move the fluid block into the control volume. So whenever some work is done on this block, basically, so work done on fluid is stored as some form of energy, is stored as some form of energy, is stored as some form of energy that is called flow energy. That is called flow energy actually. That is called flow energy actually here. So this excess energy will be available with this fluid, because when the fluid is coming in, some work is done on the fluid and that work is getting stored in this mass actually here, okay? So therefore when this system is inside, the mass will have this kinetic potential internal energies. Along with that, it will also have this special energy which is called the flow energy in open systems. Clear to all of you? Okay. So please type in the chat box, is this clear to all of you? Everyone. So please type in the chat box, did you understand? To maintain the flow, the fluid has to do some work, okay? And that work is stored as energy in the fluid. That's what we call the flow energy actually. Fine. So please type in the chat box, is this clear to all of you? So basically flow work is nothing but flow work, you can see flow work is nothing but work done by the fluid to maintain its own flow, to maintain its own flow actually here, okay? So the work done by the chat box is working, just a minute, I think charts are not coming. Yeah, so please type in the chat box now. Yes, now they are coming, okay? Yeah. So flow work is basically the work done by the fluid to maintain its own flow, and this is stored as, it is stored as flow energy inside the fluid, as flow energy inside the fluid, and this work is given by P times specific volume actually, okay? So specific work, this specific work is given as small w is equal to P times of V, specific flow energy, okay? So specific flow work, specific flow work. So therefore you can see energy of mass inside the control volume is equal to macroscopic kinetic energy at the inlet and outlets, or basically when it's entering at inlet, plus potential energy at the inlet, plus enthalpy, plus this, if you write in extensive terms, this is U plus PV, and this U plus PV combination is what we have written as enthalpy previously. So this is equal to kinetic energy plus potential energy plus enthalpy, okay? So along with internal energy, this enthalpy is also there for you, okay? Now if you see, in case of normal case, this flow work will be absent, so that's why we have only internal energy in case of closed systems, okay? So that's how we have this energy. Therefore energy of the control volume is due to three things, actually four things. but the third and fourth gets combined as one property, which is enthalpy actually. Okay, so this is one very important understanding. Okay, why for open systems it is U, and why for why for closed systems it is U, and why for open systems this is capital H. This depends upon this flow work concept, and this flow work is excessively present for the mass which is present inside the control volume actually. Okay, so to this mass which is present inside this control volume, you have this kinetic potential internal plus this flow work which is getting stored as some energy, which is the flow energy in this case. Now if you apply this conservation for control volumes actually, so if you have a system and if you have this boundary, so if you have this boundary actually, so mass interactions will take place and energy interactions can also take place actually. Now if you see this, like the energy equation, so mass balance for any control volume, for any control volume, first of all if you apply mass conservation, in case of control volumes what happens, mass will flow continuously. So this is the mathematical expression of enthalpy. How we can define H in general, this is the total energy stored in the fluid actually. Okay, apart from kinetic and potential are due to the motion of the fluid actually, but here if you take enthalpy, this H, small h, is something like internal energy which is stored inside the fluid plus also PV. So this is the complete stored energy inside the fluid. Okay, and this is not due to the bulk motion of the fluid, this is stored in the fluid with respect to by virtue of its own energy actually. Like this U is generally with respect to chemical and molecular structure, and this PV is generally due to the flow term that is there. So mathematically this is U plus PV, but this small h, if you want to describe it physically, this is the total form of stored energy inside a fluid. Okay, because practically if you see, this kinetic energy will still exist. Okay, whenever the fluid start flowing in, there is kinetic energy here, this kinetic energy will still maintain because the fluid will move inside this. Okay, here also the potential energy will still exist because the potential energy is also defined at any instant, but this stored form of energy which doesn't change generally in this case is U plus PV. So this combination, the energy, the total stored form of energy is called enthalpy within any system in general. Okay, that's why we define enthalpy with specific terms always, U plus PV. Generally very few times we write kinetic energy and potential energy as intensive terms, but we always denote this enthalpy as specific enthalpy when we are talking about the properties actually. Okay, so now if you see mass conservation here, so when you talk about this mass conservation actually, so see here, the system will have continuous mass inflow and continuous mass outflow actually. Now let us suppose if you take a turbine or something like that, whatever the mass is going in and whatever the mass is going out, the difference between these two, if you take the difference between these two, we can write that as mass flowing in, rate of mass flowing in because it is continuous flow, minus rate of mass which is coming out is equal to d by dt of mass of the control volume actually. Okay, so this is equal to d by dt of mass of the control volume. And similarly energy conservation, so if you write energy conservation, so then in that case we know again energy flowing in minus energy flowing out across the boundary is equal to rate of change of energy of the control volume actually here. Okay, so these are two important generations, which is very simple because basically from conservation rate, inlet minus outlet, okay, so is equal to the difference is equal to the thing which is stored inside. So if something is stored inside, then mass and energy gets changed with respect to time. Now we will define something called the steady state conditions. So what are the steady state conditions actually? Because you see, generally, normally we mean this word steady. So what is the meaning of steady actually? If things are steady, that means the rate of change of those quantities with respect to time is what? What is the value of the rate of change of quantities if the things are steady? Let us suppose if some flow or any situation is steady in state, then what is the time rate of change of the quantities? 0, correct? So time rate of change of quantities is actually 0 in that case. Yes. So therefore, if you see d by dt of mass of the control volume is 0 and d by dt of energy of the control volume is also 0 actually in this case. So d by dt of energy of the control volume is also 0 in this case here. Now why this steady state conditions are very important? We deal also the steady flow energy equations. Means why this steady flow conditions are very important? Because practically all devices operate under steady conditions, okay, except in the beginning, starting the device and stopping of the equipment. Apart from these two stages, normally for 99% of the lifetime of equipment, the equipment runs in steady state conditions. Because look, why it happens? Look, I'll tell you. Let us suppose if you take a turbine for example, okay. So let us suppose if I take a turbine or any device, you can take any device. So let us suppose if you take a turbine. So let us suppose you take a turbine actually in this case. So this is inlet, this is outlet, okay. So these guys are inlets and outlets, and of course there is some shaft which is coming out of the turbine actually. So that this turbine shaft will rotate. So this shaft will rotate whenever there is some mass flow in. M dot out, and this is rotation. There is some torque which happens with the shaft actually, okay. Due to this mass flow inside, due to the blade structure and all, the kinetic energy of the fluid goes and hits the blades. So as a result, the blade will rotate the impeller and the impeller rotates, and obviously this shaft which is coupled to the impeller will also rotate actually. Now try to understand one thing. Let us suppose in an industry you are running a turbine for example. Let us suppose if mass inlet you are maintaining 5 kg per second, and let us suppose some steam turbine or something, so steam is flowing in, and mass outlet is only 3 kg per second. So what happens practically after some time? Let us suppose if you are maintaining this flow where inlet is only 5 kg and outlet is only 3 kg, then for every second 2 kg of mass is getting stored inside the turbine, okay. And obviously control volume has some limited volume. Then what happens when you keep on running this at these conditions? Inlet is 5 and outlet is only 3. Then what happens actually? So what happens after 1 kg, for every second 2 kg of mass is getting stored inside. So what happens after some time of operation? In the first second 2 kg of mass gets stored inside. After 2 seconds 4 kg. After 3 seconds 6 kg. So finally within some limited time, what happens within some 1 minute or some less time, 30 to 40 seconds, the complete turbine gets filled with mass actually. Yes or no? And there won't be any provision for the entry of the new mass. So turbine gets blocked in that case. Yes or no? Correct. So please type in the chat box. Can I say this? Yes. Did you understand what happens if these two are not same? Let us suppose if inlet is more than outlet, then for every 1 second some mass gets stored inside the control volume. So definitely what happens after some time, your turbine gets blocked, okay. So that won't operate anymore. So there will be choking problem. So that's why this cannot be the case, okay. So mass flow in cannot be more than the mass flow out. Similarly, mass flow in cannot be less than the mass flow out. So turbine cannot create new mass inside. Okay, so mass can never be created. So practically there cannot be any condition like mass flow in is less and mass flow out is more actually. Okay, just before stopping the device. Okay, let us suppose if there is some shutdown has to be taken, then what happens? We will stop the turbine. So during that small stopping time, what happens? The initially the mass will decrease and it will stop finally. Up to till then, whatever mass is there inside, that will come out actually. Okay, only in that small time interval the mass inlet will be less as compared to the mass outlet. And similarly in the starting point, what happens when there is no mass initially? The mass inlet will be more as compared to the mass outlet initially, because some time is required to fill the turbine with some volume and then it flows out. Okay, but 99% of the lifetime of any equipment, they operate under steady state conditions, because mass blocking is one very serious problem. Because what happens, I'll tell you. Let us suppose if you are sending some hot steam, for example, inside, then if lot of amount of hot steam is getting accumulated inside, okay, and let us suppose if that steam is not passing out, then what happens? This high temperature inside the turbine will keep on increasing, and practically every material will have certain metallurgical limit, and after certain amount of mass accumulation and after sufficient rise of temperature, what happens? The equipment will fail. Okay, means basically it will get burnt out, or some crucial parts may get melted. So these kind of things can happen. So that's why practically this cannot be the case. Okay, so practically mass should not get accumulated, mass should not get accumulated in the turbine. So this implies mass flow in should be equal to mass flow out. So this implies your d by dt of mass of the control volume is equal to 0, because we generally deal this steady flow energy equation, all these things, but we generally never understand why that steady flow energy equation is very, very important. Because in actual practice, all devices, they operate, 90% of the industrial equipments, they operate under steady state conditions actually. Okay, similarly energy can also never get accumulated, because that is also very dangerous. You can see, let us suppose if you are sending in, let energy flowing in is some 5 kilowatts, for example, let us suppose simply, and energy that is coming out is only 3 kilowatts, for example. Okay, let us suppose if this is the case, then what happens here is, whenever this is 5 kilowatts and this is 3 kilowatts, then for every second 2 kilojoules of energy is getting stored inside. Okay, so if this process happens for some 100 seconds or 200 seconds, then some bulk amount of 200 kilojoules or 300 kilojoules of energy gets stored inside. Or let us suppose if you take megawatts, for example, in industrial equipment level, if you write in megawatts, because generally at industries this is the level of the energies that we deal. So 3 megawatt, then what happens? For every 1 second, some 2 megajoules of energy. 2 megajoules is very huge energy. So for every second 2 megajoules of energy gets accumulated inside. Okay, so if energy is getting accumulated inside, that the temperature will rise beyond the metallurgical limits of the material and it will fail again. Okay, so that's why mass accumulation or energy accumulations are very, very dangerous. Okay, sometimes what happens, because of some blockages and all, some blocking of filters and all, normally turbine won't be very this simple. Okay, so we have seen, whenever I was with HPCL, I had the opportunity to see some gas turbines, GTGs. Okay, so there are some gas turbine generators, we are working there. Okay, so we have some 4 power plants actually, a single power plant, but 4 GTGs actually. Okay, now they have increased it 2 more this year, so 6 GTGs is totally they are operating, because complete refinery will have a lot of power requirement. Okay, like boilers, electric heaters, there will be a lot of things which are working on. So, and normally civil supply. Okay, so like in the office lights and all, everything. So to have self sustainability, there is a power plant actually inside the Vishaka refinery where I have worked. So there I have the chance to look at this turbines, gas turbine generators, compressors, okay, all the things, boilers, condensers, whatnot. We have seen all the things, pumps, we have seen a lot of things, mixing chambers, okay, everything we have seen. Then if you see this m dot in and m dot out, if you see, so mass accumulation and energy accumulation are very, very complicated things. Energy won't get accumulated generally, because energy is always accompanied with mass. Okay, let us suppose if mass is getting blocked, then only energy gets blocked actually. Okay, so this mass blocking filters, sometimes what happens, this filters and all, they get blocked, and obviously they create a very serious problem actually. Okay, the material will not fail, but suddenly the flow will decrease actually. Let us suppose if something in the turbine blocks, then how do you identify that? You will have normally very lot of control valves, speed valves and all. PID controllers, PID controllers actually. So you'll have a lot of things. So whenever this gets blocked, then definitely the flow rate in this will decrease. Okay, so when flow rate in this will decrease, then you will come to know that there is some problem in the turbine, so we have to take a shutdown. Okay, so then we will go for the shutdown of the turbine and we will go for the maintenance of the turbine. We will open the turbines and then we will walk inside, and generally we'll take the filters. Each filter size will be, normally if you see the turbines that we have exposed, is like each filter will have a diameter of filters, like it's like a mesh. Okay, but very complicated. It has some 2 to 3 layers to avoid all the dust particles and all. Each diameter will be something like 7 to 8 meters. Okay, so 7 to 8 meters is such a big, almost one length of the room size, filters. So that big filters are there, we have to clean them actually. Clear? And I think the stages of expansion is like in compressor we have seen it's like 14 stages intercooling there. Okay, 10 normal low pressure stages and 4 high pressure stages. So 14 stage intercooling. We'll see this intercooling and all very important concepts again when we deal this Brayton cycles and all. When we talk about the compressors, we will have a much detailed understanding of the turbines actually. Okay, turbines, compressors, everything, every power equipment. So if you see, this energy accumulation is also dangerous, because energy accumulation, you can write energy should not get accumulated, because accumulation of energy increases the temperature of the volume, the temperature of control volume beyond metallurgical limits, actually. Okay, so they increase beyond the metallurgical limits in that case. That's why both these are dangerous. This implies the rate of change of energy inside the control volume should be made 0. That's why these steady state conditions are very, very important actually here. Okay, so if these are important, then the flow, if things are happening at steady state, then the flow is called steady flow, of course. Okay, so if the flow conditions are steady, steady, then rate of change of mass of the control volume is 0, and rate of change of energy of the control volume is also 0 in this case. Okay, so rate of change of energy in the control volume is also 0 actually in this case here. So if rate of change of control volume is also 0, this implies the flow is steady flow. The flow is steady flow in that case. So now if you apply the mass conservation, m dot in minus m dot out is equal to rate of change of mass of the control volume actually. And now if this term is actually 0, then this implies m dot in is equal to m dot out. So generally that we will denote with m dot, mass flow handled by the devices like turbines or compressors, whatever. So this is m dot in is equal to m dot out. Similarly, the energy equation B, energy conservation, so energy flowing in minus energy flowing out is equal to rate of change of energy of the control volume. So in that case again this term is 0, so this implies energy flowing in is equal to energy flowing out. So energy flowing in is equal to energy flowing out, and this is the energy equation of steady flow. That's why this is called steady flow energy equation. Steady flow energy equation. Steady flow energy equation. Now, depending upon different types of energies which are available, we will write the terms in energy input and energy output actually here. Okay, so this is the steady flow energy equation. So practically how we generally write that. Okay, so at the entry, at the inlet of the control volume, so let us suppose if we take the control volume for example like this, so you can see here now when you have this as the control volume, the control volume, so here there is an inlet and here we have an outlet. Okay, so then you can see this is m dot in and this is m dot out actually in this case. So try to understand, as I told you, energy flowing in, so energy of the control volume, you can see we told kinetic energy plus potential energy plus enthalpy actually. So this implies, let us suppose if mass flow is m dot in for example, so this implies energy flowing in is equal to m dot half times of m dot v in m dot in into v at the inlet square plus half times of, or generally m dot times of g times of z1 actually. So let us suppose here the bulk motion of the fluid is at a velocity v1 at the inlet, which is v inlet, and here it is going out at v outlet actually. Okay, so v out, and with respect to some reference, so with respect to some reference like this, you can see this elevation is at a height of z1 and this elevation is at a height of z2 actually, z2. Okay, so this is z1 and that's z2 actually in this case. So now if you calculate this kinetic potential plus this enthalpy, let us write as m dot in z in, let us write, so m dot in into specific enthalpy at the inlet. Similarly, energy at the outlet is equal to energy flowing out is half times m dot out velocity out square plus m dot out g times of z out, which is the energy in terms of potential which is flowing out, plus m dot out times of specific enthalpy at the outlet. Apart from this, let's see, let us suppose some heat interactions and work interactions are also there for example. Then what you will do, let us suppose if there is some heat interaction to the control volume, there is some heat which is flowing into the control volume and some work which is coming out of the control volume for example. Okay, these are also some there. So H is the energy stored, so how can we consider that in E in, because during this energy which is in the control volume at any point is due to the inlet, understood, because of this flow the energy is getting stored inside. Okay, so when you are writing at this inlet point, so let us suppose if you are writing at this inlet point for example, the energy which is present at this point, by that time already the enthalpy got accumulated inside the fluid. Okay, means the flow work has already got stored inside the fluid, so that's why we can consider the enthalpies. Clear, Pooja? When we are writing the steady flow energy equation here, when you take this inside the control volume, by that time when the fluid has entered the control volume, already the flow work got already stored as some this enthalpy PV combination inside the fluid. So that's why when the fluid is entering, the fluid enters, the entering fluid will already have that enthalpy. Okay, That's why we are considering the enthalpies actually. Clear? Energy which is flowing in is actually equal to the complete stored energy here, right? So that's why. So this out. So let us suppose if you also have these two energies, what we are writing is only with respect to the fluid motion. So externally from surroundings, you can have some heat interactions, energy interactions in terms of heat and volume. So let us suppose if you add that some heat is flowing out, I mean heat is coming in and work is going out of the device, for example. Okay, let us suppose, because in case of turbines and all, generally we have this work interaction, some work produced by the turbine. In case of boilers, what happens, some heat gets generated. So let us suppose if you take these things, that in general if some heat is getting transferred and work is getting transferred here, since we are taking heat as heat addition, so that why if in this equations heat added is taken as positive, heat rejected is taken as negative. Similarly here, this W dot, we are expecting in general that work is coming out of the device, so work done by the system is positive and work added is negative actually. So now if you equate these two things actually, so this implies from steady flow energy equation, from steady flow energy equation, from steady flow energy equation, m dot in is equal to m dot out, which is equal to m dot. At the same time, energy flowing in is equal to energy flowing out. Now if you equate these two terms, the right hand sides of these two terms, because energy flowing in and energy flowing out both should be same actually in case of a steady flow. So this implies energy flowing in is equal to energy flowing out, which implies, so what is the energy which is flowing in? Half times of m dot. I am removing this m dot in and m dot out because both are same actually. So half m dot v in square plus m dot g z1 plus m dot h1 plus q dot is equal to half m dot v out square plus m dot g z out plus m dot h out plus w dot actually. Okay, so work interaction of the control volume, and this is heat interaction of the control volume with the surroundings. Let us suppose QCV, WCV, you write for example, because they are external interactions. So external work interaction with the control volume. So now if you see, if you slightly adjust these terms that are on both sides, what you can write here is, you can write Q dot minus W dot of the control volume is equal to half times of m dot into v out square minus v in square plus m dot g times of z out minus z in plus m dot times of h out minus h in actually here. Okay, so h out minus h in is what you can write. So if you clearly observe, this is nothing but the difference in the kinetic energy of the fluid at outlet and inlet. Yes or no? Because half m dot v out square is nothing but the kinetic energy at the outlet, half m dot v in square is the kinetic energy at the inlet. So this term actually corresponds to the difference in the kinetic energies of the fluid at the outlet and inlet actually. Okay, so final minus initial, so we can write this as delta kinetic energy dot, because this is rate of kinetic energy, plus rate of potential energy change at inlet and outlet, and that's delta h dot actually here. Okay, so this implies you can write this equation as Q dot of the control volume minus work interaction of the control volume is equal to delta Ke dot plus delta Pe dot plus delta h dot actually. Now if you divide this complete equation with mass flow rates, if you divide this complete equation